Okay, so we talked about this last class, which is we've got some finite poles, but we don't have enough finite zeros to terminate our root locus, right? Remember the mantra, start at a pole, end at a zero. So what we need to do is we need to figure out how do we approach those additional zeros at s equals infinity so that we can complete the root locus. And what we determined is, or came up with our last class, is a way to determine what those asymptotic angles need to be. So we said if it's plus or minus 180, piece of cake, you don't have to worry about it. We just know it's never leaving the real axis. Whereas the ones that have a non plus or minus 180 degrees, those actually will approach at infinity. And if those look like they're going to cross the j omega axis, you can use one additional piece to refine your root locus. And that's where the root locus actually crosses the j omega axis. And fortunately for us, we know how to do this because we did Routh-Hurwitz prior to this. So we know how to do a Routh-Hurwitz. And if you recall from a Routh-Hurwitz, if we have an entire row of zeros, not just the first column, but an entire row of zeros, we build the auxiliary equation, which goes one row above, and then we get the coefficients from that auxiliary row, and then we set that row, or set that equation equal to 0, and then we solve for the roots of that system. So here's the summary. Did I go too quickly? Maybe a little bit quickly. How about, I'll do this one. Can you tell me the Routh-Hurwitz? Can we do the Routh-Hurwitz for this? Let's do it. So bring up whiteboard again. Of course, whiteboard quit on me. I didn't know that. Let's see how good we are remembering Routh-Hurwitz. Everybody feeling good about it? It's not necessarily going to be on the next test, right? So you may have thought I forgot about it, but it's still there. All right. So what do we have to do for Routh-Hurwitz? What are we doing a Routh-Hurwitz of or with? Or on? Very good. It's a characteristic equation. So we need to get the characteristic equation for this. So we need to do the closed loop transfer function, right? So that's going to be g over 1 plus gh. And then the numerator of the denominator is going to be our characteristic equation. So, of course, we crop that out. It's s plus 4. All right, so this is going to be s plus 3. And let me multiply this out. So s squared plus s times s squared plus 6s plus 8. I'm just multiplying that denominator out to kind of get it ready so I can do my equations. And then I have, so this is what I struggled with the other day. So we have s to the 4th. I have a s cubed and a 6s cubed. So that's 7s cubed. Now I need to go with the s squareds. So I have 8s squared, and that's it, right? I don't have any other 8s s squared. Oh, no, I have 14, sorry, because I have s times 6s. So that's 14 s squared. Now I got to go s singles. And that's basically it, correct? So s to the 4th plus 7s cubed plus 14s squared plus 8s all over 1 plus okay, so now I'm going to go ahead and do a common denominator, and I'm only going to really focus on just this part here because all I really care about is the numerator there, right? We know that this and this will cancel it out. So what I end up having is my characteristic equation is going to be s to the 4th plus 7s cubed plus 14s squared plus 9s plus 3. Now, got to be careful, right? Because I also have a k out front here, correct? Because if I look back over here, I have k. So if I just do the root over what's here, I'm not going to get any value of k that's going to be variable. So I need to make sure my value of k is over here. So I will append this to say the real characteristic equation, s to the fourth plus 7s cubed plus 14s squared plus s times 8 plus k plus 3k, right? And I wrote it as this over here because I'm pretty much ready to do my Ruth Hurwitz. The k came from here. It's part of the Ford loop gain, right? It's g. So this is the g1 times g2. They're in cascade with each other, so you multiply them out. Right?
So the k is on, so it's ks plus 3.
K times s plus 3, the quantity s plus 3. Yep. All right, so here are my rows. S to the fourth. Give myself as much room as possible. S cubed, s squared, s to the 1, and s to the 0. Now I'm going to start putting in my terms. 1, 14, and 3k. 7, 8 plus k, and 0. So now I'm ready to go ahead and do my first calculation. Negative 1 over 7 times, let's see, it's 8 plus k minus 7 times 14, is that 98? So I did the determinant there, right? I just combined it. And that gives me S2. And then if we do this other one, we should just end up with 3k, correct? Not correct? Am I going too fast? Do you need me to do the 3k number, or do you feel confident you could do that one? Anybody? Let's just put it up over here. So it's negative 1 over 7 times the determinant of 1, 7, 3k, 0, right? So we have negative 1 over 7 times 1 times 0 minus 21k. The 7 and the 21 divide out, and you end up with 3k. I'm going to just expand this a little bit so I can simplify this down a tiny bit. So what I end up with is 90 over 7 minus k over 7. All right, so now I'm going to do this term over here. So my S1 term, I'll just put it over here because I'm running out of room. So I have, so that's equal to negative 1 over 90 divided by 7 minus k over 7 times 7, 90 over 7 minus k over 7. And then I have 8 plus k and then 3k. Now you can see why I moved it out, right? Because I'm going to have a lot of calculations. So this is, I'm just going to put this in parentheses because I'll deal with it in a moment. So this is going to be equal to 21k minus, and maybe I should put these back under the 7 just to make it easy. So it's going to be 90 minus k over 7. So I have 90 minus k over 7 times 8 plus k. Right? And this is the whole thing is times 8 plus k. So now this becomes, and I'm going to move the negative sign in here. All right, so I have that mess that's in there. So keep going. So invert and multiply, and I'm going to put the negative 21k under a common denominator. So I have 7 divided by 90 minus k. All of that times 144k negative plus 90 minus k over 7 times 8 plus k. I can cancel out the 7. And that's pretty much all I can do to simplify it down, right? Not much else that I can do. So this is going to be my final answer over here. So let's zoom out over here. So my S1 term becomes, let me give myself a little room, and so I'll erase these and move this down. So this is going to be equal to minus 144k plus 90 minus k times 8 plus k all over 7. And then my S to the 0 row is just going to be equal to 3k, right? Oh, yeah, over 90 minus k. Yep, sorry about that. All right, so now all I need to do is make this a row of zeros. And if I do that, what I see is once that I have this value of k that makes that go to zeros, then I can steal from over here. So all I need is 144k negative plus 90 minus k times 8 plus k. That has to equal 0, right? So let's see. So I got to expand this out. So 8 times 90 is 720 minus 8k plus 90k, k squared, and this is minus 144k. That equals 0. So I have 82k, so I have k squared and minus, let's see, what is that? Minus 82, so that's 62k plus 720. Now I got to take the roots of that. I got to take the roots of that to solve for the value of k. So let's bring up MATLAB. So roots of 1 minus 62 and 720. So I've got 2. I've got 45 and 15. So anywhere between there, it should give me a value of k. So let's plug in 15.47 whatever. Let's just call it 15.5. So k equals 15.5. And so now I'm going to use the previous one, which was 90 minus k over 7. Oops, and 3k. This multiplies by s squared. That equals 0. You substitute your value of 15.5, and you're going to get complex roots there. Okay? Do you need me to do more to figure out the roots, or do you feel like you can do these yourself?
But then, since you have two values of k, what is
It probably, it's a possibility that it would cross it again. So it's a possibility that you would get, well, let me back up. We had the second value of k. Think about that. I'm not sure. I'm not sure the value of second value of k is normally only have a single value of k. That cancels that out, but because we have an s squared term here or k squared term, you've got 2 roots. So I don't know. I'd have to think about that more. Let's just assume it's the 15.5, so we don't have to spend a lot of time, but that's how you can find the 0 crossings. Okay. So we did that problem, and here is the summary. Get there at some point. Whoop. So we know that the root locus, because complex conjugates, has to be symmetrical. The root locus starts at a pole and ends at a 0. Your open loop transfer function, if you have more poles, finite poles than finite zeros, then you actually have to calculate your sigma sub A unless it's equal to 1. If you only have one pole, then you know because of that symmetry, because of this. So if n minus m equals 1, then you really don't need to calculate that asymptotic angle. And why don't you need to calculate the asymptotic angle? Because you know it's going to be 180 degrees. Because you can't leave the j omega, you can't leave the real axis and still be symmetric. So I would say this is a caveat only if n minus m is greater than 1. Do you need to calculate this? If n minus m equals 1, oops, said 1 and I wrote 0, then is plus or minus 180. And who cares what sigma sub A is, right? Because you don't leave. So where do you don't even care where the asymptotic angle is. So you don't care where that point where those asymptote leads. Another key one, order on the real axis, order the poles and zeros. Just walk from right to left, odd, even, odd, even. And the root loci only lives between to the left of an odd number. Okay, not to the left of an even number, but only left to an odd number. If you do need to break away from the real axis, you're gonna go ahead and substitute in your value of k, take the derivative of that because that's the max and minimum point, and set that equal to 0. And then you can solve for some points and valid points where those root loci leave the real axis. Those are going to be valid breakaway points. If you start out at complex poles or you end at complex zeros, then you have to calculate angle of departure or angle of arrival. Just depends on which one you do. And then we can do the root curve. So how do you design this? So we're going to develop a root locus for a problem. And we're going to determine a range of k. Remember, we're using this as a design characteristic so that we make sure that our percent overshoot is less than 20%. So do you remember our j omega axis when we came up with something that looked like this? That was because the inverse cosine of that theta, or the inverse cosine, or the cosine of theta, was equal to our damping coefficient, remember? So if we want it to be less than 20%, that means you calculate your m sub p, you know it's 20%. Once you know what m sub p is, you can solve for zeta. Then you're going to plot a line on here. And as long as you stay, in that region, because it's bounded by both sides, you're going to have an overshoot of less than 20%. Okay? All right, so here's an example. We have our g of s minus 2 squared plus 4 squared all over s plus 2 times s plus 4. So we already know that if we don't have a value of k, we're going to have an unstable system. Or will we? We've got 2 zeros in the right-hand half plane. Is that an unstable system? No. It's still a stable system. We can have as many zeros as we want in the right-hand half plane, but that doesn't affect stability. But the reason why the zeros are included here is because we know we want to cross into the right-hand half plane because we want our system to get higher and higher levels of under damping or less and less damping. So the root locus rule, let's start with the easy one. We plotted the poles and the zeros, finite poles and zeros. Now we got to use some intelligence. And we recognize that we have 2 finite poles and 2 finite zeros. So do we have to calculate any asymptotes when our poles approach a 0 at s equals infinity? No, because we're going to terminate at finite zeros. So theta A and sigma A are invalid, not necessary to calculate those. So our next step is moving along is we start to number the poles and zeros. So is this number 1 or is this number 1? Is it the top one or the bottom one? Yeah, that's a trick question. You only number odd and even poles on the real axis. Because if you're determining if it lives to the left of an odd polar 0, that's only for the real axis. So these are irrelevant because you're not on the real axis. So anything that is not on the real axis, you don't label. You only do these. So that's 1 and 2. It lives to the left, lives over here. And it goes away from over there. Now we need to calculate our breakaway point. Looking at that. And we probably have to calculate our angles of arrival, correct? Anything else we could get? How about where it crosses the j omega axis for a little bit of a refinement for our root locus? So remember what I said. You go through the process and you can kind of see already what I need to calculate. I don't need to calculate theta A and sigma A. Doesn't apply. So don't waste your time doing that. I do need to calculate here, 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 and the j omega crosses. Okay. So let me erase, show you. Kind of just talking through it. Now I calculate my breakaway points. So what is the value of K? Plug in here. So I'm going to do my dk with respect to ds is just the derivative of -1 over gh. Take the derivative of this and you end up with this here. Remember, I only care about the numerator, so I set that equal to 0. When I set that equal to 0, I have either -2.8 or 5.28. So now we got to put our thinking caps on. Out of those two, which one do you think is right? The -2.88 or the positive 5.28? -2.88, why? Yeah, you got to break away where there is existing root loci, right? If I break away over here, there's no root locus. So what am I breaking away from? There's nothing there to begin with. So my breakaway point isn't applying. And if you double check it, you also get a K that gives you a -2.5. So I don't even need to calculate the -2.5. I'm going to throw that away just from the word beginning. So -2.8. Now I've got my angles of arrival and departure. Here's my calculation for sigma sub A. Remember, you're just calculating the angles from any test point. And how do you approach here, right? So you're just beyond there. So you calculate your first angle, 45 degrees. The -90 you get from over here. The 45 you're going to get because, let's see, is it this one? And the -33.7 is this one. Does anybody remember? Or can you tell me how to calculate 45 degrees? Yeah, how did I get 45 degrees? I need this angle, right? And don't I know that this goes over from 2 to 2? So that goes 4 in that direction. And it goes from 0 to 4 in that direction. So what does Oscar say? The tangent of theta is equal to the opposite over the adjacent. So if you take the inverse tan of 1, you get 45 degrees. Help me out. I forgot how to do math. How do I get this angle again? Suffering from amnesia. We'll call it P at 2 and P at 4. What is it? Inverse tangent of the opposite is 4. That doesn't change. And the adjacent is I got to go from 2 to 4. So 6. What's the inverse tangent of 2/3? Amazing. 33.7. I don't need to calculate this one here, right? We know it's 90 degrees. It's straight up. And then remember that has to equal the plus 180. So when you do that, this comes in at 168.7 degrees. So you rotate 168.7 degrees. Okay, and you can do the same thing for the second one. Let me move this out of the way so you can see. Oop. Now, hopefully you can see all those calculations. So what I'm doing is I'm pushing you a little bit to say, how do I calculate these? Now we can actually draw those. You can see them in the slides. Hopefully when I print these, all these animations, the final slide does show up, correct? With all this stuff on it, I think. Yeah, okay, good. 168.7. So here's the crossing for the j omega axis. So now we got to do our characteristic equation. So we get our closed loop transfer function. We end up with k plus 1 s squared, 6 minus 4k s, 20k plus 8. Do our Routh-Hurwitz table. We force this to be equal to 0. So what does k need to be? 1.5. What's that? So once you know that, you put 1.5 here and 1.5 here, and then you build your auxiliary equation. And when we do that, we end up with an S of 3.9, S equals plus J. So that is what it looks like. That is your root locus. Here's what MATLAB would do. And here you can see that for my zeta, right? I want a zeta of 0.456. So I didn't calculate the damping coefficient. Remember, that's just calculating M sub P. So we need to be zeta to be greater than 0.456. When we take the inverse cosine of 0.456, do we go up and down or down as we increase 0.456? Remember, the coefficient, if zeta gets to, let's say it equals 0.8. Do you have more damping or less damping at 0.08?
More. Well,
It's more damping, right? Exactly. So at 0.4, it might be doing this. At 0.8, it's maybe doing something like this. It's setting out faster. Because once we get to a damping ratio of 1, the system is critically damped, so it's no longer oscillating at all. So getting closer and closer to 1 means you're getting to a critically damped system. How does that translate into this pole zero map here? What happens to my angle? The angle of that zeta line as I get closer and closer to 1.
well, I guess for the reference, yeah. So
Goes down, doesn't it? Which is exactly what we expect, because once we get a zeta of 1, where should the real poles live? And when you increase your value of k, where would the poles exist? Yeah, they'd be somewhere here on the real axis. You don't have any complex conjugates when you have no damping, right? It's all real numbers. And so MATLAB, you have the ability of actually displaying that, or you can just draw it by hand. So take the inverse cosine of 0.456, and what do you get? A cosine of 0.456 times 180 over pi, 62.87. This angle here is 62.87. If you look at MATLAB, what do these lines correspond to? Different what? Different damping ratios. These terms here are all zetas. So this one that is here was drawn by hand. That angle is almost 63 degrees. And then the same thing over here. This is 63 degrees as well. So K had better be less than 0.41. Because as I increase K, which direction do I go? Go to the right? How do you know? Remember our mantra. Start at a, and end at a, and K goes from 0 to infinity. So at K equals 0, I'm over here. So this is K equals 0, or around 0. At K equals infinity, I go over here. So as I increase K, it better be going in that direction, right? So that's why K had better be less than 0.41. Not greater than 0.41, because greater means I'm getting closer and closer to those zeros.
So if K is when K is 0.4.
Say that again?
At what point is K 0.4?
Right when it crosses that zeta equals 0.456.
Oh, so when I cross the zero, that point now K is not.
Yep. And MATLAB has the capability, if you have the control systems toolbox, it actually tells you what the value of K is. It's 0.41. That's what the gain means, 0.41. Come on, this is pretty cool, right? It's tying in a lot of stuff. It's confusing, but you're like, wow, okay, I start to see where all this stuff is tied together. It all ties together. You can also do a root locus if K is not in the standard form, but ultimately what you want to do is you want it to be so that it's your last term. So you're going to monkey with it a little bit. Don't have to worry about that in this class. We're always going to assume K is that last term. So you can see here, we're moving it around, but we're just transforming it to get that value of K to be up someplace in there. Where over here, it's not in the middle. It's in the middle, it's not at the end. So yeah, I won't do too much on this. That's it. So lab was tough, huh? I didn't get anything from Conlon, so oh, okay, that's fine. All right, let's see. I don't know why I was it lab 7?
Yeah.
Where is it? Okay. What's the question?
I think we all got, so we all got the text function, we all graph this, the function, and I mean, I think we just got background, once we had to do like our log find or.
Even from the beginning, right? So, you have your function line, and then you go to value, so you have as and as we to the element, it's fine.
Yep.
And then, you might find the locus, yeah, the locus, and then, do the, let's say, you plug in the value of the dumping ratio. Usually, which one?
We use that for, right?
Yes, the F grid, kind of. Yeah, you use the S, yes, the S grid. So you put the 0.6 and 9.
Yeah.
And then you find the thing, but then now, from there, that's where things are getting now tricky, because now, what I was thinking, maybe you now have to use the R find.
The R find?
I think yeah, R find. To find the hole within that of the region,
Yep,
and then from there, you do.
that's it. That's all you had to do.
But then this. You can ask, even now, even then you ask to find the, so instead of using KP to define the previous step, if using the MATLAB subplot. I don't know how to do the subplot, and then also,
Where are you looking for
the.
the subplot?
Yeah, so using the KP to define, just like the approach, the using KP to define the previous step, so the step up using MATLAB function,
Yeah,
and then, subplot, and then I don't know, how do you use subplot? And then also from there, everything, that's about the whole difficult, and then.
okay. So all you needed to do was now try plotting for a specific value of K sub P and then seeing what the time response would be. So you would actually didn't even need to use Simulink. You could do all this stuff in actual MATLAB. So all this is asking you is over here is with this value of K sub P, can you get the zeta and the mega sub n? Do you actually get a stable system, or does it have a percent overshoot less than whatever the value of the greater for 0.26 is? So you could actually calculate it, because that's what a second order system, all that zeta stuff that we did, that's because of it's a step order, it's a step response. So you're looking at the response to a system because of a step input. And so you were just plotting that to see, does it have a 10% or less overshoot? So does it go to more than 1.1 of its final value? And does it take more than 0.15 seconds to get to the 2% settling? So those are functions you can actually use. They're built into MATLAB to actually do that.
And then also how to estimate the error, how do you estimate the error?
The steady state error, final value theorem. Or you can use the ESS equations we did, right?
Yeah, I mean,
You knew the system type. What type of a system is this? It's type 1 system. So just go to the tables and figure out the error for a type 1 system.
yeah,
It wasn't that hard. It was just using a lot of stuff in MATLAB to do it.
oh, and then, which means to find the, what's again, the. Make it look very.
I'm not trying to. It literally is just using the stuff built into MATLAB, because MATLAB has, as long as you have the control systems toolbox, you literally just, that's what I did when I wrote this lab, is I gave you all the key commands that you probably haven't seen to actually do the calculations. And then the step input, I think it's the LTI, the linear, I think it's the linear time invariant function that actually does the plots for you. So when you're in MATLAB, if you type in LTI, let's see, I think it's LTI. It brings up another toolbox. Whoops. Okay, so what is the control systems toolbox for that? What is it? LSIM? No, I think you can plot. So there's some subplot stuff here. Step. So you actually just type in step, and then it does it that way. And so those are built into MATLAB. So if you type in, you do your transfer function, right? So we've done transfer functions here a bunch of times. So then you just type step of whatever that transfer function is, and then you'll see it. You'll see its response characteristic. And then you can actually bring out what's the percent overshoot, all that stuff. It'll actually plot it. We can do that, but I don't know what the numbers are. Does anybody remember the numbers for the transfer function?
Yeah.
All right, so let's do sys equals transfer function. What is the numerator coefficients?
3,1,250.
250 like that?
No, so 1,200. That's one.
3, 1,000?
31,200.
Oh, 31,250.
Yeah.
Okay, that's the numerator. Then the denominator is, no, see, I just need the coefficients.
One.
1,
5. 3,750. And then 0.
is that correct?
So,
Busy. So this looks like error blows for forever. For a step input. Is that correct? Is it an unstable system? This just continues to rise up. I don't remember it rising up for forever. Those, but let's see.
yes, in similarly it doesn't rise. So it's definitely.
So you have 0. This looks like a, yeah, so this, maybe it's just not enough time. It does, it looks like it continues to increase forever, but if that's what you get, that's what you get. I would have just double checked these numbers. They seem a little bit high to me, but I'm not sure.
In similarly that get going after.
It oscillates, yeah.
Something like that.
You should be able to do it in step 2, but okay. And then, yeah, it could be that this is just for some reason giving some goofy result. I'm not sure. I'd have to look into it. But it really was just use the commands. It's like almost step by step.
And then now, how do you estimate the potential?
You don't estimate it, you actually read it off the graph. So you know what the final value is, right? Then you know what the peak value is.
Yeah.
So you just normalize it to that, and that you just use that as a ratio. So take your peak value, subtract the steady state value, and divide out by the steady state value.
So the
Here's, let me show you. I would here, if I have any system, so here is my steady state result, and here is my peak. To get my percent overshoot, right? It's going to be the peak minus the steady state divided by the steady state times 100. So you can actually read that off the plot.
and then so that you can also can you also see the error of the
Yes, so the error would be, so this is here, but what would be the actual error? So this is the steady state, but my set point is down here. So the error is between, let me erase this line. The error is between here and here. So anytime after 5 tau would be what your steady state error would be. But I would just use the steady state error tables to calculate it. But you can read it off a plot. This is your set point, and this is what you've got, and the difference between the two is the error.
because in the formula the error it goes up, it goes down to 0.
Yeah, so that means that 0 should be 0. So the error, so if you're looking in Simulink, I'm not looking for, what you just told me was error of t, if you're giving a curve, right? I said, give me ESS. That's not a time domain variable. That's a final value. So that equals a number where this is going to equal a curve. But it's time variable. But the final value should be 0. If this is not 0, then there would be a problem. But you can use the final value theorem to determine.
So the final value that would be that I have to so the final value for the function or for the
No, just use the ESS approach. Remember that the case of P approach? Because if you remember, when we built those equations, we actually used the final value theorem for that already. But just use your steady state error calculations. It sounds like maybe the TA wasn't as prepared as he could have been, so that's okay. All right, any other questions? Because this is all that's going to be on the exam next week. I've already posted the exam 3 review. So Tuesday we'll do an exam review. Wednesday we'll have the test. And Thursday we'll go over the exam. And then the following Tuesday, we don't have a lot of time, but we'll introduce Bode plots. We'll do some Bode plot stuff to show you the easy way to calculate Bode plots.
Oh, and then also from the lab, when I use S3, I'm gonna get the it's going to give me the poles and the gain, right?
Yeah, it should. So S-grid should give you. It should give you, if I can get there, this part right here.
Oh, S3, it does only, so it gives you kind of the region where you get that.
Yep.
And then, oh yeah.
Then you hover, then you pick a point, and then it'll give you that information. Yep.
And then now when I use the arm of time, that's one that gives you the point, the gain and the.
Yes, and there's exactly. Yep.
Now what do you do with the pole?
That's just your final answer. You need to calculate your value of K. So it calculates the value of K, and then it just tells you what the poles are. So you can check by hand if that is a satisfactory result. The poles you don't need anything with. You can just, instead of having to plug it into your characteristic equation or your open loop your transfer function, you just know what the poles are going to be at that value of K. So it's more information than what you need.
Oh, we just need the K, right?
You just need the value of K.
Oh.
Yep, because that's what you're designing. You're designing a system with a value of K, and then the poles are whatever they need to be to meet the design criteria. But K is ultimately the only thing you can vary. Okay. Anything else?
Hey, Paul.
All right, well, that's all I
Can you hear
had
me?
for today, unless there's no further questions.
You can't hear us on
Have
the
a
call.
wonderful day.
Oh, great.
And I'm not sure why the audio is not working. Can anybody else try talking? Because I can't.
Hey, Paul, can you
Howard's
hear
tried
me?
to talk a couple of times, but I can't hear anything.
I
Giannis,
want
can I
to
hear you?
type in the chat. Hello?
Might be the speakers here. Hold on. There's a question. Can you try talking now?
Yeah, can you hear me?
Oh, yeah, there we go. Yes, go ahead.
I'm just wondering if we can extend the submission for the lab because it's on the test day.
Well, doing the lab will help you, but I mean, I can certainly push it off. When would you want it to be? Friday?
Friday, it's good for me.
That's fine. I'll ask Conlon to extend it to Friday.
All right, thank you, Paul.
Sure. All right, anything else? All right, well, nothing else. Have a great weekend, and I will see you all next week. Take care, everyone.